Okay, starting 1.1 and 1.2 and starting AP Chemistry, girls. Okay, I promise I will embed fun things as well, but my goal is to make sure that we are successful first and foremost. Okay, so in 1.1, we're going to be going over moles and molar mass and what those mean, right? Those were very key ideas that came from grade 11 chemistry. So some things that you'll notice is that I actually embed this from the actual AP document about what they want you to learn from these sections of the unit. So the learning objective here is to be able to calculate quantities of a substance or its relative number of particles using dimensional analysis or the mole concept. So if we were to take a look at this, what we are looking at here is that we want to be able to calculate that moles is equal to mass over molar mass, right? We want to be able to say that moles is also equal to number of particles over Avogadro's number, which we're going to go over in a bit. Now, on your reference sheet, they actually have this equation given to you already. They write it slightly different, I believe. No, they don't. Right? But on your reference sheet on the first page, you scan through it, it does have that equation given to you. The N is equal to M over big M. Okay? They do not give you the second one. This is not given. And we're going to do examples of those in a bit. So some essential knowledge is that since we cannot count particles directly, there has to be some sort of connection between masses of substances and the number of particles that they have. And then the other one is that Avogadro's number is that source of connection, right? So Avogadro's number is given to you as well on the formula sheet. And if you take a look at it, I want you to go and try to find where Avogadro's number is, right? One of the things is that I want to make sure that you guys know how to read your reference sheet, right? Because then it's useless. Because even if you know it's there, if you don't know where to find it, it's tough, right? So if you look through it, it's on the right-hand side in the middle. There it is. So right-hand side, it's almost like it's like a grid. Right? It's on the right hand at the very bottom of that. And it says NA, and that's Avogadro's number. 6.022 times 10 to the 23. Yep. Yeah, absolutely. Okay, so the next thing we're going to talk about is mass spectrum, and there's actually not a lot you need to know about it. It's just essentially the way that we get isotope percentage to obtain isotope percent experimentally. And you don't actually need to know a lot about this. You just need to be able to read a mass spectrum graph, right? And you just need to kind of know what it's used for. So with that said, let's talk about some of the things we learned last year or even the year before. So atomic mass versus mass number. What is the difference? One of them has to do with subatomic particles and counting them. One of them. Lola!
No, they're both. No, they're both.
Not both of them. One of them is.
The atomic is all.
So close. Grace. Yeah, essentially. Yep, yep. Right. And then atomic mass is the weighted average. So remember when we did average atomic mass last year, right? With the little summation symbol that looks like an M on its side, right? That's what atomic mass is. So when we say what atomic mass is, right, we can say, first of all, this is what we see on the periodic table. On the periodic table. And the other thing is that it is the weighted average measurement of mass, right? So an example of that would be something like if we had on our periodic table the symbol for carbon, and underneath it, let's say we have carbon like this, it's written with a 12, we have our C, it says 12 point, well, actually I should say 6 up there, 12.01, like that. That's what it would look like on the periodic table. That 12.01, that is your atomic mass, right? So it's the weighted average, right? So if you were to weigh 1 mole of carbon, it should roughly weigh 12.01 grams. The opposite of that, or kind of analogous to that, is your mass number. And your mass number is different because it tells you exactly the number of protons and neutrons in a element. Okay? So number of protons plus number of neutrons for a specific isotope. So as an example, right, we might have an example where we have carbon 12 versus carbon 14, right? And they're both isotopes of each other. And those values are rounded whole numbers, and those are your mass numbers. I'm actually going to use a different highlight color so that's not being mistaken for the other one. Let's rewrite that. So carbon 12, carbon 14. And I'm going to put maybe a pink. Let's do that. Carbon 12 like this. Ooh, very nice. It's a mass number like that. Okay. So when two different atoms or two elements have the same number of protons, but different number of neutrons, that's when we get isotopes, right? And this because isotopes don't all exist in equal amounts, right? That's why we get this decimal value, right, for the average atomic mass. And that's why on the periodic table, the weight of it is not a whole number. It's because it's the average of all the different types of naturally occurring isotopes that could possibly exist for that element, right? So when we see on a periodic table that carbon has a mass of 12.01, right? It's 12.01 because, we have this percent of carbon 12 and this percent of carbon 14. And when you weigh them all together as an average, they get 12.01. All right, and here's just a bit of a picture if that helps, right? You can see how the weights might differ from each other because there's extra neutrons or, less neutrons or so forth. And the calculation that we learned for calculating average atomic mass was the following. We learned that we can calculate average atomic mass. I'm going to write AAM for average atomic mass. AAM. AAM is equal to, and we said the sum, so that's the sum symbol, of the atomic mass multiplied by its percent abundance. And this is for each isotope, right? So regardless, if you have 3 isotopes, you do that 3 times and you add them together, right? So that's what this symbol means here, right? Sum symbol, add together. So as an example, we have 3 isotopes of silicon that occur in nature. We have silicon 28, silicon 29, and silicon 30 with given percent isotope abundance. So we see here that for silicon, oops, 28 here. It has an atomic mass of 27.97693. We see here that we have silicon 29 at 4.68% with a mass of 28.97649. And we see that we have one more here. Let's do the pink one at 3.09% and a mass of 29.97377. So those are your three different varieties. So what you're going to be doing is you're going to multiply the percentage by the mass and then add that to the other percentages multiplied by mass. So this is what it will look like when we put it all together. So we get the first one is 0.9223 multiplied by 27.97693. Keeping in mind that you want to make sure that you're writing it in decimal values, so converting that percent to a decimal. But the thing that I noticed a lot of people doing last year is that whole thing, that whole chunk is added to the other things multiplied together. So you almost think about it as if there's brackets between the three different isotopes. So I'm going to go ahead and do that. So I have 0.0468 times 28.97649. And then we're going to multiply that or add that to the last isotope. So if it helps, I'm going to actually put the brackets in a different color so you can see that each isotope is separated, right? And that's what you add together. Because I was seeing like addition symbols and multiplication symbols between every single number, right? So we just want to make sure that we have it separated correctly. So this one's 0.0309 times 29.97377. Those multiplied together give us the following, right? I have my calculation here. I pre-did it. So I get 25.80 plus 1.36 plus 0.926. So notice that I am rounding to the nearest number of sig figs when I multiply and divide things. So when I multiply these first two numbers together, right, I have a value here with 4 sig figs. And so my value there needs to also be rounded to 4 sig figs, right? So it's the lowest one when you're multiplying and dividing. So this is 4 sig figs. Comparatively, right, the next one only has 3 sig figs. Yep. No, don't worry. Which is why my second value only has 3 sig figs, because those two are being multiplied together. And the lowest number of sig figs there, right, we have 3 sig figs, and then 1, 2, 3, 4, 5, 6, 7 sig figs, right? So the 3 sig figs is lower, so that's why we're going to round it to 3 sig figs. And our last one is going to have 3 sig figs as well. That's when you are multiplying and dividing values, you have to take the lowest number of sig figs. What is the rule when you add and subtract? It's not lowest number of sig figs, it's lowest number of decimal places. Exactly. Right? So if we take a look at this, what has the lowest number of decimal places? We have to round it to the nearest. You have the right idea, but it's not called the 10th. It's the 100th. There we go. Right? So this has 2 decimal places, 2 decimal places, and then 3 decimal places. So when you add these values up, you round it to 2 decimal places, which is going to be 28.09 AMU. Okay? And that's your final answer. Absolutely. Does this ring like a mild bell? Like the most mild of bells? Okay, so thank you. In order to actually get the information required to run this calculation, because at the end of the day, how do scientists actually find out what the percent abundance of an element is? Or how do they find out like what the mass is of a particular isotope? Well, there's a way to do that, and it is through an experiment called mass spectrometry, which is 1.2. Right? So this is the 1.2 material, and you barely need to know anything about mass spectrometry. I will, however, kind of go through how it works so that you can understand the graph that comes from it. So when you are measuring isotopic abundance, it goes through a machine that kind of looks like this, or it goes through a portion of a machine that looks like this. And the idea behind it is that the atomic mass, right, is going to be affected by how many neutrons and protons there are in that, in the atom, right? So atomic mass is affected by the number of protons and neutrons. And so if an isotope has more neutrons, it's going to be heavier. Now, in a mass spectrometer, isotopes are injected into a machine and vaporized, right? So that means that they are turned into gas form and shot through a tube with two magnets in it, okay? What's going to happen is that the magnetic field is going to cause the isotopes to be deflected. And if you think about, making a big turn, right? If the isotope is lighter, right, or more charged, the isotope is going to deflect more. Basically meaning the magnet and the weight of the isotope is going to affect how much it bends and the angle that it bends when it moves through this machine. And that allows it to be separated at a detector, right? So when this happens, the detector can say, oh, like 10% of this atom weighs this much. 20% of this atom weighs this much, right? And essentially what you end up getting is a graph that looks like this. So all you need to know for mass spec, okay, is how to read it. When a mass spectrometer is used, you get data in the form of a mass spectrum. And a mass spectrum gives you two pieces of information. It tells you the atomic or the isotope mass. So gives mass of isotope plus percent abundance. So if we were to take a look at this graph here, okay, and let's say instead of, we're going to cross out part of this question, right, because we're going to read the data ourselves here, okay, because you're sometimes going to be expected to do that. So if we were to take a look at this, right, this data here, we're going to pretend that this 84 doesn't exist down here because we can't read that properly. Let's say that there was only 3 bands on this graph. Okay, so not the 84. They're telling you that there are 3 isotopes here. These are 3 different isotopes. 3 different isotopes. So your first isotope has a mass of 86 AMU. If you want to know, whoa, go back. If you wanted to know what the percent abundance of that isotope was, well, now you can look at the other side of the graph and see what percentage line it is at. So what would we say that is at roughly? Yeah, around 10%. I will always say though, you always want to read to 1 decimal past what is given. So they give you up until the whole number, which means you can actually read it up to the 10th decimal place. So the 86 here, I'm actually going to use a different number color here. The 86th isotope has an abundance of roughly 10%. So we'll write 10.0% because we want to read to one extra decimal place. Then we have an isotope with an atomic mass of 87, right? And we can read that abundance to be maybe, let's say, 5, 6, maybe 6.8. I'm going to say 6.8%. I stopped myself there. Yeah.
How close? Like, would you give us?
I would give you anything, like, I would say I would give you anything between 6.6 to 6.98-ish. Or not even. Actually, sorry. I would have given you anything from like 5 to 8%. Right? So it's pretty wide in terms of the margin. If you told me it was 9%, that's not accurate, right? But you wouldn't lose like a full mark. It'd be a half mark, if anything. And the last one is 88, right? And so the isotopic abundance here, I say maybe is like 80, I don't know, 82.0%. No idea. Something close to that. And so now we have all of our percent abundance and all of our masses needed for our isotope. And we can use that to solve this question. And so if we were to do that, we said average atomic mass is equal to, and we can go ahead and calculate it. It is the sum of the isotope mass times its percent abundance, which gives us 82 or 86. Let's start with that. I was going to start with the percentage. So 86 times 10%, which is 0.100, added to the next isotope, which is 87 times, and this time we have 6.8%, so we're going to say 0.068 plus, we're going to do the last one, 88 multiplied by 0.820. We're going to go ahead and plug that in. So we have 86 times 0.1 plus 87 times 0.068 plus 88 times 0.820, which gives me 86.67. Although technically I didn't do the sig figs right, so I have to.
If you do all like that, you get the like small decimal place.
So that's why you can't actually do it all. Yeah, so I'm just doing it again. This is 8.6 plus, and then 87 times 0.068 equals 5.9, because the two sig figs, plus 88 times 0.820, 7.2. I feel like I did something wrong there. What did I do wrong? 10%. Oh, 72. Sorry, that's why. I was like, this doesn't add up to anything close to 80. Okay? So, right, when we multiply it, we took the lowest number of sig figs, which was 2 in each of those from the 86, 87, and 88. And so when we add it, we take the lowest number of decimal places, and the lowest number of decimal places is the whole number. So when we add this together, we're going to do 72 plus 5.9 plus 8.6, And even though the answer ends up being 86.5, because you have to round it to the nearest whole number, your final answer is 87 ammu. How do we feel about that?
Maybe given, let me do it. So we can give the 100%.
Um, so it would probably be easier to read, right? Or you would just be given the percentages. Yeah, this one's not a great one. I was just running out of options. Okay, so a few more pieces of information before we kind of go through sig figs again, because that's kind of what we're going to go through here. Because this is just a lot of review, right? So the isotope that is typically used or that is used for establishing a standard for the atomic mass scale is actually carbon 12. So carbon is essentially what all atomic masses are based off of, right? So carbon 12, right? And the idea behind that, right? If I have my notes here, I don't know, where did it go? Right, so the idea behind carbon 12 is that this is what all of mass spectrometry was based off of, because they realized that 12 grams of carbon exactly had an equal number of protons to neutrons, but then they also realized that is equal to 1 mole exactly. So carbon is usually used as a standard. And so if we were to take a look at these questions, right, these were pulled from a textbook, an old one, right? Other things that you might have to keep in mind besides that is your ability to count the number of protons, neutrons, and electrons in atoms. So if you were given something like zinc 65 there, right? So we're doing 2.27. I'm going to change my color. So we have zinc 65. Would you be able to determine the number of protons, neutrons, and electrons? What does that 65 at the top tell you? Nope. Nope. It's the mass number. So the number that you see there, that is your mass number, right? So if you remember atomic notation back from grade 9, 10, right? This is your mass number. So this is the number of protons plus neutrons, right? So if we were to take a look at this, right, that tells us that this zinc isotope, right, has 65 protons and neutrons added together. How do we figure out how many protons it has? Where can we look to find the number of protons in an element? Periodic table, atomic number, exactly. So take a look, find zinc. Tell me what the periodic or the atomic number is. I want you to get used to looking at your periodic table. Alice? 30. So go ahead, take a look at 30. So we know that from the periodic table, right, that we have 30 protons, right? So if we know that we have 30 protons, how many neutrons do we need to have if we have a mass number of 65? 35. How many electrons do we have? 30, okay? And we need to have the same number as protons if you want it to be neutral. For neutral atom. So I want you to try with tungsten next. So you see the W there. So we have 184 W. So that's tungsten. I want you to figure that one out. And then once you're done that, I want you to try this AP style multiple choice question that involves the use of a mass spectrum, right? So this would be something equivalent. So this, we need to look at this and try to figure out which is. So it's a matter, right? So there you have it. The more you look at the periodic table, the more you're just gonna know where things are.
I feel like sometimes they're a little unintentionally like this.
Yeah. So while you're attempting the AP style question right after this with the mass spectrum, I'm just gonna fill this in. So tungsten has 74 protons, question mark, right? So remember, this is from the periodic table. And since we have a mass number of 184, that means the number of neutrons need to be 184 minus 74, which gives us a total of 110 neutrons. Did I do my math right? That was in my head. Beautiful. And then the electrons are going to be the same number as protons. Right? So you should have gotten 74 protons, 110 neutrons, and 74 electrons. So I want you to take a look at this question. I'll give you a few more minutes. On the AP exam, the understanding is that for the multiple choice section, there are 60 multiple choice questions, 60, and there's 90 minutes. Meaning that you have roughly a minute and a half per question, right? Some questions you will answer far faster than 1 minute and like 1.5 minutes, right? There are actually many questions that will be to go to something like, we'll give you an element, like kind of proton stuff. Okay, boom, right? With that said, I will go through some strategies for doing the multiple choice section. There's something called a triple pass where you go through it 3 times, right? The first time you do all the questions that you know you can do, like you read the question and then you answer it, right? Any question that you feel like you could do if you have extra time, you mark it with a star, and then you just move on, right? You don't even attempt it, right? You take a look at it, right? And if you feel like it'll take you more than a minute and a half, you start it, move on. Any question that you feel like you have no idea what it's like, going to be a guessing game to you, really, you mark it with a different symbol. And then once you go through all of it, on your second pass, you attempt the ones with a star. And on your third pass, you can do whatever time is remaining with the ones you don't know. Okay? So I will walk you through this. So the whole idea behind a mass spectrum is that it is telling you how many isotopes exist at a certain percentage, right? So it is telling you that you have, the lowest isotope. This is your lowest isotope that exists, can only have a mass of 92. Has a mass, sorry, not average, of 92 AMU. What is the highest mass that an isotope of this element has? 100. right? So this is the highest mass. So realistically speaking, you can't have an element that is given to you here that has a mass or an average mass that is lower than 92 or higher than 100, right? Because there'd be no way for you to get that number by doing an average, right? Because if you're meaning, it's like, think of it this way. If these were your scores on a test, right? What would be the average score, right? If these are the scores that you got on different tests and these are the weightings of the different tests, what do you think your average would be? It could not be anything below 92 and it could not be anything above 100. So in that case, we take a look at the elements. So there are 4 elements there, starting with niobium. So niobium there, right, is Nb, right? And if you take a look at it, Nb has a mass of 92.91. So if you want, you can even write in there 92.91. That's the mass that you got, right, from the periodic table. The next one, there's molybdenum. Can someone take a look and tell me what molybdenum? What's the mass of molybdenum? 95.94. How about uranium? It's on one of the bottom ones.
Is it 9?
Or no. What's uranium? 0.0. And how about, I don't remember what this one's called. Ceophium? No idea.
It doesn't.
No. Oh, no. Beautiful. But it's higher than uranium, right? So, yeah. So greater than 238 and 03. So immediately, we know it cannot be C and it cannot be D, right? Those averages would not make sense in the context of that mass spectrum. Between the two of these, which one is it more likely to be based off of the idea that this is like an average that you are taking? No, molybdenum. Yes, exactly. Niobium is the other one. Because if it was niobium, right, you would expect the weighting of things to be far more shifted towards this average area, right? So that's how you would read this. And so the answer here would be the molybdenum. Ooh. And we're going to end the lesson here. Once I can reverse what I did there. Right, so the answer here will be molybdenum. So in terms of what the expectation is for homework, right? Some of this is going to be review, right? And we will take up them together, but I will ask that you do questions, let's see, not 1 right now, not 3. We'll do 4, 5, I actually want you to do 6 and 7. It has to do with accuracy and precision, but 9, 10, and 11. Actually, leave out 6 and 7 for now. We'll do that next time. So for homework, if you could do questions 4, questions 5, questions 9, 10, and 11. The nice thing about 9 and 10 is just counting number of sig figs. Okay? So with that said, when you are done your homework, the answer key with my notation in it is already there for you, right? But we can also discuss if you are still confused in class. With that said, are there any questions, comments, or concerns? I know it's not the most exciting first day of school for chemistry, right? With that said, I hope you find some joy in it one day, if not this year. Have a wonderful rest of your day, and I will see you on Thursday. Oh,